Hello everyone. Today we are going to find the expression for the normal stress and the tangential stress on an inclined plane of a rectangular member that is subjected to two mutually perpendicular stresses. That you could see that sigma 1 and sigma 2. Okay, there you see the rectangular member that is subjected to two mutually perpendicular stresses, sigma 1 and sigma 2. In the previous video, we were able to find the expression for the normal stress and the tangential stress on an inclined plane for a rectangular member that is subjected to one stress, that is sigma 1 only. But today it's going to be two stresses, sigma 1 and sigma 2. Okay, and this is going to be extremely useful to develop failure theories. So I'm going to do this a little slowly. So please bear with me if you're already very familiar with the rudimentary concepts. So I'm just going to do this a little slowly. So to begin with, there you could see the rectangular member. So what I mean by rectangular member is it's simply a structure, okay? It's simply a structure with a certain thickness, okay? And there you could see that this rectangular structure with a thickness T, it is subjected to two mutually perpendicular stresses. There you could see that it is subjected to a pull on either side, that is sigma 1 on either side. And it is also subjected to a vertical pull, that is sigma 2 on either side. Okay, the uniformly distributed forces, the stresses are manifesting because of the uniformly distributed forces. So sigma 1 is because of the uniformly distributed load. That you could see the uniformly distributed load shaded in yellow, the little black arrows that you see. So that indicates the uniformly distributed load. Okay, fine. So to begin with, I want to first define the expression for sigma 1. So right here, what is the expression for sigma 1? It's simple. Stress is load by area. So that is very easy. So let us say that the load is P1. So what is the load? It is the load, it is the resultant of all these little guys. That is P1, and it is going right through this red arrow. The resultant goes right through this, okay? And that is P1, okay? Divided by the cross-sectional area. And we know what is the cross-sectional area. It is, oh my goodness. We know what is the cross-sectional area. It is height. It is AB, okay? So this is AB. So this point is A, and this point is B. So it is AB into thickness. All right, so this enables us to compute an expression for P1, which we will be using. So P1 is equal to sigma 1 into AB into thickness. So we will be using this expression. So first I defined what is sigma 1. Okay, now we know that it is the P1 is according to the principle of transmissibility. So first, let me draw this triangle separately. So here we go. So this is our line AB. And this is our line inclined plane AC. Okay. All right then. So we know that the load is, according to the principle of transmissibility, it is pulling in this direction. So according to principle of transmissibility, the load is transmitted across its line of action, which means that the load P1 is also acting here. Okay, so let me represent that by a slightly different color. So maybe this red. So that is P1. Okay, now you could resolve this force P1 into two components. One tangential to this inclined plane AC, another one perpendicular to the inclined plane AC. We know that this is theta, so this angle should be 90 minus theta. Okay, now I'm going to resolve the force into two components. One tangential, so which is going to be P1 cos 90 minus theta, which is what is P1 cos 90 minus theta? Cos 90 minus theta is sine theta. So let me write that directly. And the vertical component, which is P1 sine 90 minus theta. What is sine 90 minus theta? It is cos theta. Now I got the force. which is P1, that is transmitted and it is acting on the inclined plane AC, and that force is resolved into two components. One is the component that is acting tangential to the inclined plane, and another one is the acting normal to the inclined plane. Okay. Now this enables me to define the normal stress and the tangential stress. Very simple, right? So what is the normal stress? Normal stress is sigma n, and this normal stress is due to sigma 1. Okay, this is due to sigma 1, and normal stress on this inclined plane. So you are defining normal stress on the inclined plane AC, okay, is equal to, which is load, which is P1 into cos theta, divided by the cross-sectional area, which is AC into thickness. That's the area, that's the inclined cross-sectional area. Okay, fine. So I hope you are able to imagine that. Yes. Now we know what is the value of P1. Mathematics is just like moving objects. So what I'm going to do is I'm just going to take this value of P1 and substitute it here. So sigma 1 is now given by sigma n is now given by sigma 1 into AB into thickness into cos theta divided by AC into thickness. So I can cancel this thickness on either side. I know what is the value of AB by AC. Okay, you see that cos theta in this triangle is adjacent side, which is AB, divided by hypotenuse side, which is AC. So I can replace this AB by AC by cos theta. So I will be getting sigma 1 into cos theta, which is cos square theta. So that's the expression for sigma n on AC due to sigma 1. Okay, so let me put a box. So that's the expression for the normal stress on the inclined plane due to the horizontal stress sigma 1. We're going to find the expression for the tangential stress on this inclined plane due to sigma 1. So that is very simple. In exactly the same manner, tangential stress on on AC due to sigma 1 is equal to the tangential force, which is P1 into sine theta divided by the cross-sectional area, the inclined cross-sectional area, which is AC into thickness. Okay, so we know what is the value of P1. Mathematics is just like moving objects. It is sigma 1 into AB into thickness. So it is sigma 1 into AB into thickness into sine theta divided by AC into thickness. Thickness in the numerator goes away, denominator, yes. AB by AC is cos theta. So now I got the expression for the tangential stress due to sigma 1, which is sigma 1 into sine theta into cos theta. I can multiply and divide by 2 to get 2 sine theta cos theta can be written as sine 2 theta, right? So maybe I can suspend that for a while. Fine. So this is the expression for the normal stress and the tangential stress. In exactly the same manner, I'm going to now derive the expression for the normal stress and the tangential stress. This time it is not due to sigma 1, it is due to sigma 2. Okay, so due to this guy here. Okay, so let me redraw this just to emphasize. Let me redraw this. Here we go. So this is our rectangular member, and you could see this is our line AB and this is our line AC. So it is A, B, C. Okay. Now let me represent the UDL maybe slightly by a different color. So here is the projected area. If I just draw a perpendicular line from C, it goes like that, but not very well. Okay, so this is the line it meets here. Okay, all right then. So this line, this distance should also be equal to BC. Okay, so I'm going to localize my attention only on the load that is acting on this region, okay, on this region. So the load that is acting on this region, let me say it is P2, okay. Now I'm going to find the expression for P2. What is the expression for P2? It's simple. Stress is load by area, so load is stress, which is sigma 2, into area, which is BC, right? That's the area, BC, into thickness, okay? Into thickness, okay? I hope P2, the load is stress, which is sigma 2, into area, which is the same as BC into thickness. So that gives us the expression for P2. So we will be using this expression for P2. So this load, the small UDL, the resultant of this load will be going in the downward direction. So this big green line represents the resultant force, okay? Resultant force P2. Now you can resolve this resultant force P2 into two components. One is the normal component. Another one is the tangential component. One is the normal component. Another one is the tangential component. So before that, this is theta. So if this is theta, so this should also be theta. So what is the normal component? It is P2 sine theta. What is the tangential component? It is P2 into cos theta. Now we got the two components. Now all I have to do is find the expression for the normal stress and the tangential stress. That's it. So the expression for the normal stress, sigma n, this time it is due to sigma 2 is equal to the normal load, which is P2 into sine theta, divided by the area, which is AC into thickness. I can just substitute the value for P2 now. Just substitute the value of P2. You will be getting sigma 2 into BC into thickness into sine theta divided by AC into thickness. Thickness in the numerator and the denominator goes away. So what is BC divided by AC? It is opposite side. This is hypotenuse side in this right angle triangle. So opposite by hypotenuse is going to be sine theta. So we can say that sigma n due to sigma 2 is equal to sigma 2 into sine theta is sine square theta. So that's the expression for the normal stress due to sigma 2 on the inclined plane. Now we're going to find the expression for the tangential stress. So the tangential stress due to sigma 2 is equal to tangential load, which is P2 into cos theta divided by the area, which is AC into thickness, the inclined cross-sectional area. Not the cross-sectional area, but the tangential area. So I'm substituting the value of P2. P2 is equal to sigma 2 into BC into thickness. So it is sigma 2 into BC into thickness into cos theta divided by AC into thickness. So I can cancel the thickness on either side. We know that BC by AC opposite by hypotenuse is sine theta. So I'll be getting sigma 2 into sine theta cos theta. So that's the expression for sigma t due to sigma 2. Okay. So we have computed individually. Now we have to find the total, right? We simply have to add the sigma n due to sigma 1, which is the normal stress on the inclined plane due to sigma 1, plus the normal stress on the inclined plane due to sigma 2. Okay, that's what we are going to do, to find the total. So now we are going to find the total. The total normal stress on this inclined plane, the total normal stress, sigma n total, and you know where the story is heading. It should be the total due to sigma 1 plus sigma n due to sigma 2, okay? Both the stresses. So what we will be getting, sigma n total, we are just going to add the two expressions, which is sigma 1 cos square theta, which is sigma 1 into cos square theta, plus sigma 2 into sine square theta, sigma 2 into sine square theta. Okay, we know what is the expression for cos square theta can be written as 1 plus cos 2 theta divided by 2. So that's what I'm going to do in the next step. Sigma 1 cos square theta can be written as 1 plus cos 2 theta divided by 2. And similarly, sine square theta can be written as 1 minus cos 2 theta divided by 2. So in the next step, you can pull the terms that are common outside. Sigma 1 can be pulled outside. So in that case, you will be getting sigma 1 into 1 plus, okay, sigma 1, I'm sorry. If you just take the common terms outside, you will be getting sigma 1 plus sigma 2 divided by 2 plus sigma 1 minus sigma 2 divided by 2. It's common for both the cos 2 theta. Okay. Yes. So that is the final expression for the normal stress acting on the inclined plane. So in exactly the same manner, what is the total tangential stress? It should be the total due to the first sigma 1 and sigma 2. So this is the inclined plane. This is the inclined plane, but we have to be a little careful this time. You see, the first total is going in this direction, and it is given by, look at the expression. The first one is going in this direction, and it is given by the expression, you see. Yeah, the first one is going, where it is, it's here. It's going in this direction, and it is given by the expression sigma 1 into sine theta cos theta. So let me represent that. The first one is going in this direction. It is given by the expression sigma 1 into sine theta cos theta. If you look at the second one, second tangential stress, it's going in this direction. You see, it's going in this direction. So it is going in the opposite direction. It's given by sigma 2 into sine theta cos theta. So that's the expression. So the total tangential stress will be sigma 1 sine theta cos theta minus sigma 2 sine theta cos theta, because they are moving in the opposite directions. So I can pull the common terms outside. So I'll be getting sigma 1 minus sigma 2 into sine theta cos theta. Now I can multiply and divide by 2 on either side, both in the numerator and the denominator. So I'll be getting sigma 1 minus sigma 2 divided by 2. 2 sine theta cos theta can be written as sine 2 theta. So that's the expression for the total tangential stress. All right then. Now, if you look at these two expressions, it tells us when the normal stress can reach the maximum. Well, there are two ways to find out when the normal stress, at what angle the normal stress is going to reach the maximum. The first way is if you just plot this sigma n along the y-axis, and if you plot the theta along the x-axis, we know that it's just going to vary in a sinusoidal fashion, right? Like this. So you can just use the technique of maxima and minima, and you can say that at the maximum point, d sigma n divided by d theta should be equal to 0. So if you just do that, which we will be doing, you see, if you just do that, if you just differentiate this equation, if you find d sigma n divided by d theta, you will be getting sigma 1 minus sigma 2 divided by 2. Cos 2 theta, if you differentiate, it is minus sine 2 theta into 2, and that should be equal to 0. So this gives us sine 2 theta should be equal to 0. Sine 2 theta will be equal to 0 when theta is equal to 0 degree, right? At that time, it's going to become 0. Or when 2 theta is equal to 180 degree, in that case, no, not 180 degree, I'm sorry, when theta is equal to 0 degree, or when theta is equal to 180 degrees. So just excuse me. Or when theta is equal to, say, 90 degree. Theta is equal to 90 degree. When theta is equal to 90 degrees, so this becomes sine 180 and that becomes 0. Okay. So at two angles, the value of the normal stress is going to become maximum. One is theta is equal to 0 degree. So if you go back to this diagram, so this is where the theta, it becomes 0 degree, and this is where the theta becomes 90 degree. Okay, theta becomes 90 degree. So at these two angles, the normal stress is maximum. Two values of normal stress. When theta is equal to 0 degree, the maximum normal stress should be sigma 1. And when theta is equal to 90 degree, when theta is equal to 90 degree, the maximum value of the normal stress, when theta is equal to 90 degree, the maximum value of the normal stress should be sigma 2. Okay, so we can check it. So here we go. We will go back to the expression. When theta is equal to 0 degrees, so cos 0 degree is 1, so you will be getting sigma n is equal to sigma 1 plus sigma 2 by 2 plus sigma 1 minus sigma 2 whole divided by 2, because cos 0 degree is 1, so you will be getting sigma 1. So at 0 degree, which means that you are talking about this plane. Okay, this is where theta is 0 degree. And when theta is equal to 90 degree, cos 180 degree becomes minus 1. So if you substitute for cos 180 degree minus 1, so what is that you will be getting? You will be getting sigma, let me write that here, sigma n is equal to sigma 1 plus sigma 2 by 2. And if you multiply by minus sign, it's minus sigma 1 plus sigma 2 whole divided by 2. So you get sigma 2. And theta becomes 90 degree, right? 90 degree. This is 0 degree. And it becomes a 90 degree when the plane is rotated like this. Okay? So this is theta is equal to 90 degree. I'm talking about this particular plane. Yeah. So at these two planes, the value of the normal stress becomes maximum, and the values are sigma 1 and sigma 2. Okay. And what about the shear stress? When do you think? This is one way by which you can find the maximum normal stress. The other way to find the plane at which the normal stress becomes maximum is the plane where the shear stress becomes 0. Okay. So the plane where the shear stress becomes 0 is the plane where the normal stress becomes maximum. So here is the expression for the shear stress. Okay. And if you just equate it to 0, so it becomes sigma 1 minus sigma 2 divided by 2 into sine 2 theta becomes 0. So in that way, you can say sine 2 theta is equal to 0. So here again, theta is either 0 degree or theta is 90 degree. At these two planes, the value of the shear stress is going to be 0. So the place where the normal stress is maximum is also a place where the shear stress is 0. And those planes, the planes where the normal stress becomes maximum and the planes where the shear stress becomes 0, those planes are called as the principal planes. Okay. Now, at what angle the shear stress becomes maximum? That's very simple. The shear stress becomes maximum when this value sine 2 theta becomes maximum, and it becomes maximum when 2 theta becomes 90 degree. Okay. When 2 theta becomes 90 degree, or when 2 theta becomes 270 degree. Okay, so it becomes maximum either at 90 degree or when the value of 2 theta is 270 degree. On these two angles, the value of the shear stress becomes maximum, right? So the angle at which it becomes maximum, 2 theta is 90 degree or 2 theta is 270 degree. At these two angles, it becomes maximum. So the value of the shear stress becomes maximum at 45 degree, or it becomes maximum at 135 degree. Okay. So here we go. So here is our rectangular member. This is the reference line, and it becomes maximum at an angle of 45 degrees. So at this angle, the value at this plane, the shear stress on all these planes, if you draw all the planes that are parallel to these planes, the shear stress is maximum, okay, on all the planes. Okay. Similarly, it becomes maximum not only at 45 degree. So there you can see. Okay, it also becomes maximum at 135 degrees. So say for example, you have rotated by 45 degree. So continue to rotate by 135 degree. Then at that angle also the shear stress becomes maximum. So this is, if this is rotation by 90 degree, okay, and after rotation by 90 degree it looks like this, and you just have to rotate another 45 degree, right, to reach 135 degree. So like this. So on this plane, okay, the shear stress becomes maximum on these planes. So these planes will experience the maximum shear. These planes are going to experience the maximum shear. Okay, and the maximum value of the shear stress is sigma 1 minus sigma 2 divided by 2. Okay, and you could see that the ductile materials primarily fail due to the shear, and the brittle materials primarily fail due to the maximum normal stress. So we will delve deeper into the topic when we discuss theory of failures. Enough for today. So thank you all for your patience.